Hello GGS 300 and welcome back to the third lecture for GGS 300 Quantitative Methods for Spatial Science. Today we're going to be focusing on descriptive statistics. I will be setting the second assignment this week, which will be based on this work, which will cover essentially theoretically within this lecture, and then we'll actually get into some kind of practical empirical applications for these methods in the laboratory session, which will follow. Okay, so hopefully you've all managed to submit the previous assignment now, which I'm pretty sure you have. So that was the first assignment, and again, this will be a fairly standard 7-day period for you to basically turn this around, and all of the content for what you need to submit will already be within the practical that we follow through this week, so it should be fairly easy for you to kind of convert that into hopefully a very successful assignment submission. I did speak to a few of you regarding the work last week, which was great. So it was really nice to reach out to some of you and chat. And please don't hesitate if you do have any challenges with the work to send me an email, and hopefully we'll be able to get this all sorted so that you can perform well on this course. So today what we're going to be focusing on is a kind of introduction to descriptive statistical concepts and techniques. Okay, so we kind of touched on this very briefly in the previous couple of sessions where we're kind of talking about kind of the approach to statistics and the different approaches that you could take based in terms of whether you're using kind of a descriptive approach or a more formal statistical hypothesis testing approach. And this is really going to form the first core part of the first third of the overall course. Okay. So what exactly are descriptive statistics? And really what we're talking about here are summary statistics, okay? So they provide numerical or quantitative metrics which describe the kind of overall general characteristics of a data set. So you can kind of think of these in scientific terms as a set of statistics which you want to produce as your first port of call when you receive a set of data. Okay, maybe it's a new area that you're working on and you don't understand it yet. Maybe it's a new data set that's been handed to you. What you want to do is basically produce all of these summary statistics for all of the metrics of interest that you have, so that you can start to build a picture yourself of how different metrics are distributed, how they relate to one another, so that you can start to kind of crunch through the real world data on the problem that you're trying to investigate. Okay. And as I will emphasize within this course, there really are underlying statistical properties which exist across all types of data that we collect. Okay, so whether I go out and I basically sample houses in Fairfax and we look at the house prices, or whether we're measuring the speed of vehicles on a road, there are probably underlying statistical characteristics which are shared across those different areas of investigation. Okay, so if we can then understand what those characteristics are, we can basically use them to our advantage. Okay. So what do these two things have in common? So height measurements. So let's just say we took every single person within, I wish, the lecture room that we were operating within. So let's just assume that we took every person who's taking this module, for which there are maybe about 9 of you, and we measured every single person. Okay, and then let's say that we compared that data along with, let's say we had multiple dice and we were rolling them and we were recording the outcome that we got each time over 100 different rolls. What is kind of common to this? Well, really what I'm trying to get at here is it's the distributional shape of the underlying data. Okay, so let's say that we took height measurements. This data here is actually for female adults in North America, and on the x-axis you have height in inches and you have the number of female adults. Okay, so you basically have the most number of individuals around about the height of 65 inches, and then as you go smaller or larger than that, you get a tapering off and you have fewer individuals. So you're going to have most values clustered around the average, mean, value and the median value in the center of this distribution here. Okay, so we'll touch on this within today's lecture in lots of detail. So now I just want to kind of introduce this concept to you that we can think of a system of investigation that we're interested in, whether that's height or dice rolling. We can think of it in this way, whereby we collect metrics for individual observations, whether it's your height or whether it's for the number of dice, for the total number of values that dice have produced when we roll them, and then we can basically plot them in this way. Okay, so we covered this in the previous example when we thought about histograms. And here what we're interested in is a very similar property. We're interested in the overall shape of this distribution. So height's a fairly common example to understand this, but also I just want to touch a little bit on rolling dice, because incidentally I was actually playing at the weekend Monopoly with a couple of friends, and we did look at some of the strategies for playing Monopoly, and what was interesting was they said on a Monopoly board, obviously you can be sent to jail and then you have to get out of jail, for anyone who's familiar with the concept of the game. But then the most optimal place to buy property on one Monopoly board is between 6, 7 and 8 steps away from the jail position, and that's because of the shape of this distribution. Okay, so if you have people repeatedly throwing a dice, the higher probability is that they're going to land having a 6, a 7 or an 8. So that's where you want to buy property, because if people all end up in one place because they go to jail and they have to break free of that, then most likely on their first roll to be this number of steps away from that position. Okay, so it's kind of strategic, but it's kind of nice as well, because if you understand probability in this way, then you can really kind of start to use it to your advantage in life. So whether that's playing, a fairly mundane board game, or whether that's trading on financial markets, you can start to understand the statistical properties of different distributed variables and use that to achieve some objective, whether that's, making the world a better place or just merely making money. Okay. So whenever you see these distributional shapes, which I'm going to show you today, just remember that underneath this distributional shape are a set of outcomes, okay? And where the shape is tall, that means you have the largest number of outcomes, and where it's small, it means you have the least number of outcomes, okay? So we touched on this last time, and on one side of this this diagram we have basically the kind of descriptive statistics approach towards understanding scientifically things about the world. And then on the other side of the slide, we basically have a more formalized hypothesis testing approach. So we're going to get to this later in the course, but for today I just want to focus over here. So we may identify a problem that we have, and then we may want to develop research questions for how we investigate that particular problem. And then essentially what we would do to actually try and answer those research questions is we would need to go away and we would need to collect data and then prepare that data. Okay, so maybe I say to you, I want us to go out and I want us to understand the average property price in Fairfax. And let's say we do it, in a very old school way. This is me essentially sending you out to go and try and meet valuers and get valuations for a sample of properties, okay? And then basically we can come back with that data and information, and when we can process it, we can describe that data and we can reach some conclusions. Things obviously, thankfully, have changed a lot in the last 10 years because of the explosion of data that we have. So if you're going to actually carry out that process today, you probably go to something like Zillow or some other type of online platform and basically extract all of that data with some sort of geographic boundary and some sort of timestamp information for when you wanted it, in a very kind of quick and effective way. You don't have to do what people used to do in the 80s and 90s, where you'd have to go out and collect this by hand. So I think it's almost easier for you these days because there's such an abundance of data and information for you to process for things like your dissertation. Great, so I don't want to spend too much time on this. I think the one thing I just want to emphasize is that there are differences between parameters, which generally relate to an entire population, and statistics, which generally relate to a sample from that entire population, okay? So let's say that we wanted to look at the house prices in Fairfax City. The entire population would be every single residential unit within the city boundary. and we would refer to the mean house price for that population using the Greek letter mu. Okay, so here you can see mu as the population mean, and we would refer to all of those residential properties as the population. We refer to the size of those properties. That's for the sake of this discussion. Let's just say it's 2,000 residential properties. Then that would be referred to as a capital N. Okay, and that refers to the fact it's a population because it's capitalized. This then contrasts with a sample of the population. Okay, so let's assume that we didn't want to go out and get the house price for each one of those individual houses. Let's assume that I said I wanted you to go out and randomly sample 100 properties out of those 2,000 residential properties. Then you would come back and you would have a sample size which is 100, and we would denote it here using the character lowercase n. So n always refers to the sample size. It just depends whether, if it's capitalized, it's the population. If it's lowercase, it's the sample. Okay, and then equally for the sample mean, when you actually get all of those 100 house prices and you start to work out what the arithmetic mean is for those entities, you would refer to that as x bar. Okay, so you can see here we have x as the sample mean, and the bar is indicative of it being a mean value. Okay. So x, refers here to the sample, and the x bar refers to it being a mean value. Now, that may seem new to you, and if it does, then I'm afraid you're just going to have to learn these different notation forms, and that's just simply kind of how it is. But it's important because we actually have different statistics. We have different equations to calculate depending on whether you are actually referring to the population or statistical sample. Okay, so I will talk a little bit more in this lecture about why that is, but particularly I'll give you an example within the practical for why we basically have these different equations. So if it's a sample, you're going to have more uncertainty within it, and therefore you may need to account for that additional uncertainty when you're estimating certain metrics. Okay. Great. So there's these different types of descriptive statistics. So the data set can be summarized with these three types, and I just want to quickly emphasize what they are, and then we'll kind of talk a little bit more about what could be in each one of those different areas. So measures of central tendency, measures of dispersion, so how distributed the data are, and then measures of kind of the shape and the relative position of a data distribution. So what does that all mean? Well, when we refer to central tendency here, what we're talking about is the individual metrics which represent the center of a distribution. Okay, and there's a variety of different ones that we could choose. It could be the mode, so the most frequently occurring value. It could be the arithmetic mean, or it could be the median value, so the median representing the 50th percentile kind of point within the data set. Okay, and these are single metrics, and therefore they're useful to understand in kind of a small snippet of information, but it also means that they don't give you an overall perspective of the variation beyond that point. That's where we use measures of dispersion. Okay, so when we talk about dispersion, we're interested in the spread of the data, so how distributed the data points are around for example, our mean or our median, and therefore we're able to understand more about the level of variation that's within the data. So we could have the range, which just basically tells us the distance between the lowest and the highest value. Or what we could have is the interquartile range. So we're getting a very different set of kind of more complete set of metrics when we use a box plot to demonstrate the interquartile range, because we're getting the quartile points, we're getting the mean value as well, and we're getting some outlying values all graphically displayed. So we'll be able to look at that within this lecture. And then finally, we get measures of shape or relative position. So this is just basically looking at the distributional shape for the underlying data points and asking, well, is it skewed? Does it have a particular shape to the kind of peak that's on the data? And we've got kind of quantitative metrics which can help us understand this, and we can test whether it conforms to our understanding of the normal distribution or not, and then we can use that to our advantage if it does, because it gives us a probabilistic understanding of where we think values are going to lie. And that's important because we will be covering that later within this course in the next the following lecture and the lecture after that, when we start to get into probability. So our measures of central tendency, let's start now with the mode because it's nice and easy. So the mode is just simply the most frequently occurring value. So it's something which you can very commonly use when you've got your nominal, qualitative, categorical variables, okay? Obviously, you might not be able to carry out quantitative metrics for qualitative categories, but you can look at the most frequently occurring value. You can also apply it if it is a set of quantitative data, okay? So I've got a good example down here. This is a distribution, and the mode would essentially be this highest peak in this histogram here, okay? So this is a unimodal distribution. I say unimodal because it's indicating there's just one modal value, okay? And that kind of contrasts with the fact that we could have a bimodal distribution, okay? So you could have two peaks within the data with individual values which are basically more frequently occurring, okay? Or we could have multimodal, and that could indicate that there are lots of different peaks in the data all showing different values, and therefore you need to kind of work out why that was happening. So there are two meanings. One is it's the most individual frequently occurring value, which is kind of the more stricter definition we mentioned at first. But then as we get into the kind of recognition that there could be bimodal or multimodal peaks in a data set, then we're kind of recognizing that we have this local maximum within a chart. Okay, so when we say local maximum, what we mean is that this part of the data set here has a maximum value, and there's clearly something going on in this part of the data here that we need to understand. And then over here, although there's a different overall maximum value, clearly there is something happening here that we need to try to understand in the data. Okay, great. So let's move on to the median value, which I'm sure you all will have heard of before. So this is essentially the middle value within a set of ordered values. And therefore it's the value with an equal number of data both above it and below it. Okay, so I kind of think of this as the 50th percentile point, and that means you've got 50% of the data above essentially and 50% of the data below. And that's quite different to the mean, as well. I'll show you shortly. Okay, and how we actually then calculate that. So essentially the data must be ordered from the smallest to the largest. And then essentially if the sample size is odd, well, that's nice and easy, right? Because it means that the median is just going to be the middle number within that data set, within the list of ordered values. Whereas it's a little bit more tricky if you have an even number, because it does mean that then you take the average between those middle two values, okay? So you'll need to find what they are. And I've just given you the equations here for how you calculate that. But I think that this is kind of more intuitive to most people than some of the other tests which we're going to work on. And don't worry about understanding this in practical terms. Obviously, I'll cover that later in the lecture and when we're in the practical part of this session. So let's just think about the household income distribution. So this is for 2014, so it's a little bit dated now, but I just wanted to emphasize it because we clearly have this heavily skewed data distribution, okay? And income's the kind of classic example of that, because the large majority of people are going to be earning a relatively small amount, unfortunately, and then there's actually going to be some huge outliers where, the Bill Gates of the world, the Elon Musks, those characters are going to be basically pulling the mean of the distribution well away from the median point. Here, obviously, the median distribution is this 50th percentile point here. And this is the point where we have 50% of the data lying below this line and 50% of the data lying above this line, okay? But I always think that this kind of makes for stark reading, because you kind of understand how you do get income inequality within society when you start to look at the differences in the actual income distribution levels across the entire population. Okay, so I always feel like this is kind of sobering reading, to be honest. So now we've spoken about the median, which has a very kind of clear understanding for where you have 50% of the values above it and 50% of the values below it. What about the mean, which many of you will have come across before? It's widely referred to as the average. I'll refer to it as essentially the arithmetic mean. This is the sum of all of the values and then divided by the number of values that we have, okay? So it's a nice metric, we use it a lot, but it does mean that you need to be aware of the underlying distribution, because if you have a heavily skewed underlying distribution, much like I showed you before, then our mean is going to be pulled in the direction of the skew. So here this is positively skewed. All of these values are spreading out towards the positive part. You can also have a negatively skewed distribution, although I'll talk about more about that later in the lecture. So this is positively skewed here, and therefore the average will be much higher than this 50th percentile point where the median is. The average will probably be somewhere over here in the distribution, and that's why you need to be somewhat aware of it, because that average may not necessarily be that representative when you do have quite a heavy skew. So as I mentioned before, we have those two different types of metrics depending on whether it's the sample mean or the population mean. So to get the sample mean, we're interested in getting this x bar value. So we basically need to take the sum of, so we've got sigma n, so we're referring to all of the observations within the data set for all of these xi values. So the I refers to, just think of it as the row in the Excel data set if you're not familiar with this. So it's basically saying, give me the sum of all of the values in the data set starting at row 1 for x1, row 2 for x2, row 3 for x3, so on and so forth. So when you see the I, that's really referring to the if value, which is just a statistical way for them to say any, it's an abstraction, it's referring to any data set depending on its size, okay? So it's just saying we need to sum up all of the values in our data to get our numerator. And then when we've got the sum, we then divide it by, you can see the denominator here, which is the sample size, so it's the total number of observations that we have, and then we're able to obtain the mean of the observations here, which is the x bar. So we'll do this within the practical session. Just remember that the population mean is going to be represented by mu, and mu is going to be obtained by basically taking the sum of all of the xi values in our population and then dividing by the total number of observations in our population. Okay, so it's similar in this case, the structure, it's just that we have different notation depending on whether we're referring to a sample or a population. We may not always have all of this data broken down, so this is just an example for how we might calculate a weighted mean. Maybe we've got frequencies by category and we want to understand how we then still develop a kind of average picture across these classes, these groups of data. So maybe this is when we've got the raw data missing, as I mentioned before. So the weighted mean is basically the x bar w that I refer to here. So then we have this equation for how we find this down here, which is that we need to take the sum of all of the values multiplied by the frequency count in each of the groups. So xj here is the midpoint or the average for the group, and then fj is the frequency count. And then we need to do this for all of the number of groups, okay? They need to be summed together. And then n is the total number of values across all of the different frequencies, okay? So let me give you some examples because that's kind of high level. So let's say that we have the average temperatures in DC over the summer months. So it's going to be hot, it's going to be humid, but maybe we want some kind of average daily understanding for this entire time span. So let's just say in June we have 76.2 Fahrenheit on average. We then have 30 days in that month. In July, let's say we've got 80.7 Fahrenheit on average, and we've got 31 days. In August, 81 Fahrenheit, 31 days. Okay, so to get this x bar, the weighted x bar, then we need to basically get our denominator, which is, so it's 76.2 multiplied by the 30 days, and then we need to take the summation for each of these different months. Okay, and then on the denominator, we need to sum all of the total number of days in each month, okay? So we end up with this set of numerator values here, which need to be added together, and this denominator, and we're then going to divide them, and we get 79.3 as the daily average for the entire time span, okay? So we're able to use that weighting to make an estimate for what the daily temperature is probably going to be. So we can use another example here, maybe where we're a bit more constrained in the level of data that we have. So let's use home values again, because it's, my favorite kind of go-to example, because it's tangible, it's something we can all kind of relate to, because it's, the built environment is something that we engage with on a regular basis. So let's say we have a range of home values in a city block and we want to understand what the average home value is. Let's say that we've got 3 houses in the range of 200 to 250k. We've got 5 houses in the 250 to 300k bracket, and then we've got 2 houses in the 300 to 350k bracket. We basically need to use the class midpoints for the xj values. So when we say we've got 200 to 250k, we're going to take the mid value here, which would be 225k. For the 250 to 300k, we take the mid value, which is 275k. And the 300 to 350k is the mid value is 325k. So when we then put the numbers together here, so the 225k multiplied by 3 represents the 3 houses in this bracket. We've got 5 houses in this bracket, and we've got 2 houses in this bracket. We're then able to get our numerator, and then our denominator is just the summation of the number of houses that we have, which is 10. And then we get 270, or 270k is the weighted mean here. So that must mean that our numerator over here adds up to 2,700. I think the important point to emphasize here is that this is a weighted mean as a best estimate, okay? So we don't have the actual house prices within each of those range brackets, so we're using the midpoint as an example. So this is the best estimate based on the data that we have available to us. But that gives you an understanding for how we would make that sort of an estimate. So the question, therefore, is, well, which measures of central tendency should you use in each different situation? And it's a big problem with all of statistics. Am I using the right test? When do I use the right test? These are questions which really worried me when I was starting out, because it's not clear how you make that decision, and you only get it from experience. And it's not that easy to work that out when, maybe you're an undergraduate dissertation student and you're trying to do your first piece of research, essentially. So I'm going to give you some guides, and you can use this as a good guide for the best measure for central tendency for different types of data. But you'll see that I do this persistently throughout the course. So as we get into more formalized tests, I'll be giving you flowcharts which provide you with some indication as to which the best statistical metrics are to use, or statistical tests, depending on the types of data that you have and the number of samples that you have and what your kind of purpose is, okay? So if we have nominal data, remember that's categorical data, then the mode would be the best measure of central tendency to use. So this is, how many items do you have in each category overall, and you're trying to understand which the most frequent category is, okay? So that would provide you with the mode. Or it would be best in that circumstance to use the mode. You couldn't use quantitative information easily because you might not have any. Ordinal, remember that's where you've got categorical information, but they're actually in some sort of a magnitude siding, so you've got an order in the actual underlying data. The median would be the best case in that example. And then if you have nicely normally distributed interval or ratio quantitative data, then the mean would be the best example. But then as you start to get into quantitative data that's heavily skewed, so a little bit like the income distribution that I showed you previously, then the median would be the best representation overall, because you don't want to be presenting a mean value which doesn't really represent the data underlying all of these values. Okay? So really what we're trying to do here with the central tendency is just to understand that clustering of values around the central points within a set of data values. So that's the first stage. Now let's move on to thinking more about the actual distribution of those data points and how they vary across the distribution of data points that we have. So let's start with the range, and I mentioned this before, it's kind of the most basic measure of dispersion that we have. So it's basically taking the smallest value in the data set and the largest value in the data set, providing the data at interval and ratio. And essentially it's looking at the distance between those two different data points. But the problem is that it doesn't tell you any information about how the data are clustered across that range, okay? So it's really not that useful relative to other types of distributional measures, some which I actually love. So here I'm talking about quantile deviation. So the question is, well, what's a quantile? A quantile is an equal portion of a data set, okay? And I use these all the time. I use these a lot in my data because the way that we understand population distribution across space, for example, can be thought of very nicely in terms of deciles or percentiles. So if we need to try to deliver some sort of infrastructure service, the economics of deployment of that infrastructure service is going to be highly dependent on the population density and the adoption rate, and that's going to be nicely thought of in terms of either deciles or percentiles. Okay, so if we have the median, then actually the median is basically going to divide that data set into two equal sets. So we have the upper 50% portion of the data, and we have the lower 50% portion of data. We could have quartiles. So this would be taking that median individual point, and then for each of the 50% of data, we're going to create an extra point which represents the 25% mark in each of those portions. So we have an upper 25% of values. We then have a middle upper 25% of values. We then have a middle lower 25% of values, and then we have a lower 25% of values. Okay, so it's just splitting that whole data set up into 4 portions. And then we can do the same for quintiles, setting it into 5 portions, or deciles, where we chop it up into 10. So the easy thing to remember here is to kind of focus on the first part of the word. So if it's quart, sounds like a quarter, be 4 easy sets, 4 equal sets if it's quartiles. Or deciles, obviously, I think most of you, is familiar for you. It relates to 10. I guess is it either Greek or it's probably either Greek or Latin, the etymology of that word, but it refers to there being 10 equal sets. Percent, you'll be familiar with, so 100 equal sets. Okay, so you can kind of discern what they're referring to by the name. Okay, it's logical. Interquartile range. So this is the difference between the first quartile and the third quartile. So I know before I was kind of explaining to you quartiles, it's maybe easier for me to show you here using the box and whisker plot. Okay, so this is the median point in our data. We then have the what I call the central lower portion of the data, so here up to the 75 percentile mark, and then we basically have the upper 25% of the data, which would be approximately up to this area here, although we do have some outliers above that. Okay, so the point is that graphically we're able to show with the box plot where the median value is, and then the 50th percentile of values around that. So each part of this block represents 25% of the data. So you see here we have the median, it goes up to the 75th percentile, and it goes down to the 25th percentile. Okay, so I think that's fairly straightforward for you. The whiskers, so these parts here, so I didn't refer to this as any sort of explicit indicator of the top of the distribution, because we obviously have outliers still. This whisker essentially is 1.5 times the interquartile range of the box. Okay, so it's indicative of where the majority of the values are probably going to lay, but you do have outliers beyond that. I like box plots. I think that they're a reasonably nice way to present data. So I'm going to give you an example for a recent piece that I did for the World Bank, and that's the question is, well, what percentage of annual gross domestic product would each country need to invest in 5G over the next 5 years in order to provide universal broadband? Okay, so gross domestic product is just a good way for us to measure the total size of an economy, if you're not familiar with this term. So obviously the United States has a gross domestic product of something like $20 trillion a year, so it's very large, whereas other countries are most likely going to have much smaller gross domestic products, okay, depending on how large their industrial base is and how much their households spend. Okay, so I've used box plots in this particular example that I'm giving you here as a way to actually cluster countries into similar groupings. Okay, so I actually used a clustering method here for the gross domestic product per capita, the population density, and the 4G coverage to group countries into different coloured groups. So we have 6 clusters. All of the countries here, which are in yellow, are seen here on the global map. in yellow as well. So in this kind of least developed, low-income set of countries, you can see, quite frankly, many of the poorest countries in the world, unfortunately. So we have Afghanistan, we have the Democratic Republic of Congo here, we have Sudan, we have Mali in West Africa. There are so you should be familiar with these countries and where they are on the map, okay? But then actually we can look at some of these other countries. So in the highest income group here, we have Mexico, Brazil, Argentina, China, Russia. So you should also start to see some patterns emerging for how these different groups are clustered. The key point, though, is that I've used these box plots as a way to show both the underlying data distribution, so you can see all of the little plots that I've put in here, and then I've used this as a way to show where the distribution is relative to the central mean for all of the data points, okay? So it's a nice way to show this distribution of data, but the reason why I put them into these clusters is then we're able to calculate what the cost would be within these groups, which means you kind of reduce the uncertainty. So that was just a long-winded way for saying that we crunch some numbers for how much we think it's going to cost as a percentage of annual GDP for each of these cluster groupings. So just remember that yellow is generally low income and green is basically upper middle income, okay? So these countries are getting wealthier as you move up the groups. So essentially what you have in the lowest income group is that universal broadband is going to end up being a much larger share of your gross domestic product. Potentially up to 4, 5, 6, 7, 8% of GDP you might have to invest into broadband infrastructure in order for you to deliver comprehensive coverage, which is obviously hugely unrealistic, but it's important that someone crunches the numbers. And then you kind of contrast that with the size of the GDP of some of the other countries. I mean, you could be looking at less than 1% of gross domestic product that would need to be invested in universal broadband in order to actually make sure that everyone has access to a decent internet connection, hopefully as soon as possible, but most likely, the target is for everyone to be connected by 2030, hopefully. So anyway, this is just a good way for me to kind of emphasize how you have distributions of countries within each of these clusters and then kind of compare them to each other. So that was a bit of a tangent, but I just wanted to give you a good example of how we actually use this in real world problems, okay? So the standard deviation, some of you may already have encountered this metric. It's a really nice one, actually. It's basically the average dispersion around the mean, okay? And the deviations from the mean are essentially squared, averaged, and then square rooted to put the number back in the same units again, okay? So if that's not clear now, I hope it will start to become clear as we move through the lecture, because you will see how other metrics don't always have their numbers, for example, square rooted again to put them back into the same original units. So how do we calculate the standard deviation? Well, we have both a metric. We have an equation for the sample and the population. So to get this S value here, which is the standard deviation, we need to take the square root of the sum of the square deviations. Okay, so what this is saying is we want to sum all values, and we want to subtract the mean from each one of those values. We want to square them, and then that gives us the sum of the squares. Okay, so I'll show you how to calculate this manually when we get into the practical. And then once we've got that numerator, we need to divide it by the number of degrees of freedom. So this is n, so the number of observations in the sample, minus 1. That indicates the number of degrees of freedom. I'll explain more about this later. And then once we've got that numerator and the denominator, we divide them by each other, and then we take the square root, and it provides you with the standard deviation back in the original units. We can do the same for the population. The only difference is that obviously we don't have an x bar value like we do with the sample. We have a mu value. And instead of using the number of degrees of freedom here, we just have the population, the number of observations overall in the population. So capital N. And then that gives us sigma, so this value here, which is the population standard deviation. Okay, and one of the reasons why we are essentially subtracting 1 from n here, I will explain shortly. So, the number of degrees of freedom. Why? Well, this is basically correct for small samples where you don't have much data. And remember before I said that if there's uncertainty within some of our sampling methods, we might need to change how we actually calculate some of our estimated metrics, and this is a good example. When you've got a large number of samples, the difference between n and n minus 1 is very small, so there isn't much difference. But with small samples, you basically you might be underestimating the actual population standard deviation, and therefore you need to account for this. So basically, by using this n minus 1, the number of degrees of freedom, we're able to make the denominator slightly smaller, making the n calculation slightly larger to unbias the estimator. Okay, and if that's all, if that's all gobbledygook to you because you're not familiar with this, then that's fine, because I'm going to give you an example in the actual practical today in R, where we calculate for a small sample using just the total number of sample points or the number of degrees of freedom, which is basically the sample points minus 1. Okay? Okay, great. Let's move on then. So the variance and the coefficient of variation. So the variance is the average squared deviations from the mean, and it's very much like the standard deviation, but it's not returned to the original units. Okay, so you'll notice that we do not square root again the values that we obtain here, so they're left squared. Okay, so the sample variance is, again, we're going to get the sum of the squared deviations, so we need to subtract the x bar value, the average, from all of the individual points, and then we need to square them, and then we need to sum them to get our denominator, and then we're going to divide it by the number of degrees of freedom. And because we haven't square rooted these again, they're going to stay in their squared value. They're going to stay in the larger level of units. This is referred to as s squared. Okay. And then we can see the same for the population variance. So we've got sigma squared. And again, this is going to be the same equation, just different notation. So we're going to use mu as the population mean, and we're going to use uppercase N to denote the population, the number of entities in the population. Okay. So it basically measures how far a set of numbers are spread from their average value. We can also use the coefficient of variation. So the standard deviation is an absolute measure of variability. So it's going to provide us with an understanding in kind of the original units. But it means that it's kind of hard to compare different locations at different times, maybe even those metrics which are measured in different units. So, for example, we may have 40 years worth of annual precipitation data, and that may provide us with a mean of the precipitation rate in Buffalo of 35.47 inches and a standard deviation of 4.7 inches, okay? And then we could look at the same for San Diego, and it's got a much lower mean, so there's much less rain there. So it's 9.62 inches on average. So it's definitely not like where I am now in the UK, where it rains a lot. And the standard deviation is 4.42 inches. Okay, so this is kind of, I'm going to show you now why it matters to have a coefficient of variation, because you might see those statistics and kind of be swayed by you know the large mean value of rain in Buffalo, but actually we need to think of this in a kind of a relative way. Okay, so the question is, well, which city has a higher precipitation variability? And you might instinctively think Buffalo, but not actually when we calculate the numbers. So the coefficient of variation is relative. It's relative to the data that you have. So what this basically means is that we can think of it in more of a percentage term, and that way we kind of abstract away from the units upon which they were measured. Okay, so if you have a low coefficient of variation, that means you've got less variation in the data overall. So the data, the more clustered around the mean, less dispersed. Whereas if you have a high coefficient of variation, then that means you've got far more variation, okay? And the data are less clustered around the mean, much more dispersed. And we can calculate this coefficient of variation by taking our S value, so our standard deviation, dividing it by the sample mean, and we can basically get the percentage by multiplying it so the outcome by 100. Okay, and when we do that for the Buffalo data, the coefficient of variation is 13.25%. Whereas if we do that for San Diego, the coefficient of variation is 45.96%. So there's much more variation in San Diego, okay? So just because the mean's lower, we've actually quite a lot of variation there. Whereas Buffalo is basically always wet, or much more likely to always be wet, relative to San Diego, where you could have maybe spells of drought or spells of rain, and therefore you've got a much larger standard deviation relative to what the mean is, okay? So it's giving us an understanding of what the underlying distribution of the data actually are. Okay, so we'll think about this more when we get into the practical, and I can show you in very practical terms where we look at the data, calculate the coefficient of variation, and hopefully then that'll kind of sink into your brain exactly what this means. So how do we interpret it? Well, the higher the coefficient of variation, the greater the level of dispersion around the mean. So I think it's easy for us to kind of think of this as a percentage. So here, 23% variation is going to be lower than 50% variation, okay? And this enables us, as I said before, to work across different data sets which are in different units, for example, and maybe not that easily comparable. So it's standardizing that measure of dispersion. Great, so we're making good progress. I'm on the final part of the lecture now, so soon you will be able to go off and have a think about what's been reported here. Skewness, so this really refers to the distributional shape, so it depends how much symmetry is within that frequency distribution of values. And remember, whenever I show a normal distribution shape like this, what I want you to think of is that distribution of the dice, okay? So remember, whenever I show the distribution, the outline, what it's really showing underneath is these distribution of points, okay? So if you roll 2 ones, you get 2, and that's highly unlikely relative to all of these different combinations in the middle here, where you could get 7, okay? So that's where you roll 1 6 and 1 1, or you could roll 1 2 and 1 5. And therefore, you've got a much higher probability of rolling a number which combines to 7, and that's why you have this big peak in the middle of the distribution. So I'm just recapping there, because often for people who have just come across this information for the first time, it's very easy to kind of forget, oh, what do these random shapes that Ed's showing me actually kind of represent? And obviously, this is kind of abstracting away the kind of underlying data. It's just a very simple curve to represent that you've got more data points here in the center of the distribution and fewer at the edges, and you can think of that in probability terms, okay? So you're much more likely to roll a dice where the numbers sum to a value in the center of the distribution than you are for the numbers to sum to a value at the edge of the distribution. If we have a normally distributed data set like this, then the skewness is essentially equal to 0. Okay, it means that we've got a symmetric distribution, and we've got no real kind of dispersion of data points in any one way or another. So it's kind of, you have this kind of beautiful curve, often called in fact the bell-shaped curve, because it looks slightly like a bell. Okay. Now, things get tricky, you see, when we start to have negatively skewed or positively skewed distributional points. And the reason why I want to just dwell on this for a second is because when I was starting out, would get negatively skewed and positively skewed the wrong way around. The reason why this is negatively skewed just here is because imagine this is a number line. So imagine you had 0 in the middle here, and you had positive numbers spreading over to the right, and you had negative numbers spreading over to the left, then this long tail of distribution here would be negatively skewed because it's stretching towards more negative values, okay? I think I used to get it confused because I used to think, oh, the hump of the distribution is more focused towards the positive side, and therefore this must be positively skewed. And that's not true, that's incorrect. You need to focus on the tail of the distribution, okay? So when I say the tail, I mean the long part here which stretches out. And you can think of this in terms of the long tail of hurricane sizes, for example. So most hurricanes will be of a certain size, but then we have some that cause astronomical amounts of damage, and that's why you end up with particularly natural hazards and disasters having a very long tail of events. Okay, so your Katrinas of the world, your Harveys of the world are going to be in that long tail where they caused absolutely huge colossal destruction, and then you're going to have more mundane hurricane or natural weather events causing much smaller amounts of disruption, thankfully. Okay, so this is how you think of a negatively skewed or positively skewed. So if you think of the example I just gave you in terms of the amount of disruption caused by natural hazards, that's going to be positively skewed. Okay, imagine that that's the number of dollars of damage that an event causes. Then your Harveys or your Katrinas of the world are going to be up here in the top part of this skewed distribution. Okay, so mathematically, if we refer to skewness as below 0, that would indicate that it's negatively skewed, so the tail's to the left. Or if the skewness is over 0, then we would indicate that it's positively skewed, so that's where the tail is to the right. And actually, you'll have noticed that this skewness equation down here again wants to calculate the sum of the deviations. So remember, we're subtracting the sample mean here, the x-bar, from each one of the individual data points that we have. And then instead of squaring them here, we're actually cubing them and taking the sum of them, okay? And then we can then take this numerator and divide it by the number of sample points that we have multiplied by the standard deviation cubed, okay? And that's how we get the skewness. And you'll see that there are a set of metrics which allow us to understand different things about the distribution depending on whether we are squaring, cubing, or raising to the power of 4, okay? So I've already covered most of this, but this slide is just to emphasize more about the measures of central tendency. So in the normal distribution here in the middle, we would have the mean, the median, and the mode in an ideal world all overlapping with each other. Okay, so the normal curve represents a perfectly symmetrically distributed set of data. Whereas if we have positively skewed data, they will be, like our income distribution, will have those values all skewing over to the right, and that will drag our median, so our arithmetic mean, much higher than it should be. And that would mean that we'd end up with a median in the middle here, where 50% of the values lie above, 50% of the values lie below. And then obviously this peak value here is going to be indicative of the mode, okay, so that's the most frequently occurring value. And then we can think of that in the flip reverse. So if we think about it in terms of the negative skew, it would be the same. It's just that those long tail distributions would be heading out to the left in a negative direction, and that would have the opposite effect. So it would drag our mean down, it would drag our median to the left, and the mode would remain on that most frequently occurring part of the distribution. Okay, we did a paper and we basically looked at a whole load of data. So when you use a cell phone, you are trying to connect to your closest cell tower, and your phone is doing some very clever things. It's trying to estimate the best cell tower for you to connect to, and it's recording all the time what your received signal is, okay? And often you can get big data samples off mobile phones, which you can use to understand the distribution of the cell phone signals that people have basically received. Okay, so here's an example for, these are basically the 3 main operators in the United Kingdom, so Vodafone, O2, EE, and 3. And essentially this on the x-axis is the mobile phone signal, so the higher is better and the lower is worse. So minus 20 obviously much worse than minus 5. These are measured in decibels, and that's why you have these minus values. So these are indicating very, very small levels of electromagnetic radiation being detected, so radio waves being detected here, which is how we transfer data. So your Instagram Reels is basically being sent by radio waves back into the internet when you're making an upload, essentially. Okay. And then what we've got here are different geotypes. So let's assume that this is the most populated area, so this is urban areas, and then let's assume this geotype 2 is suburban, and this is rural, okay? And essentially what we've got are the proportion of the samples on the y-axis. So we can kind of think of this as a probability of you actually being able to achieve a certain signal level. Anyway, the point I wanted to make was that you obviously have incredibly skewed distributions here, okay? So this is more indicative of what the real world data looks like when you get it. And I remember doing statistics early in my undergrad and my postgrad and my master's degree, and kind of expecting to get a normally distributed distribution. So we could use these tests that kind of, the parametric tests that you use most of the time in statistics, as you'll find out later in this term. And the data is just never normally distributed. It's always messy, messy, messy. And there's kind of the art of statistics. So this is obviously highly quantitative and highly scientific, but then there's also a lot of kind of understanding that you need to have in order to make sure that you kind of pick the right test and make sure that if you are going to change some of the data distribution, which you can do with various transformations, that you're picking the right one. And there's often no hard and fast rule for that. It's not like a very clear science for how you make that decision. It's going to come down to the researcher. And therefore, there's an element of personal judgment in it, really, which is, concerning, because you might make the wrong choice and that may influence your results, and that may mean that you give the decision maker the wrong advice. Okay, so anyway, this is just an example of how messy real world data gets. Okay, final metric now. We're almost done, we're on the home straight. So kurtosis, this measures the flatness in a frequency distribution, okay? So we've got three distributions over here. We've got the mesokurtic, which is the normal distribution, here, which is the green curve. And then basically we have the platykurtic negative flat distribution, so it's this blue one just here. So platy means broad. I always think of it as if you had a platypus, which is a fantastic animal, then you would just lay it on the bottom of the kind of distribution line, and you would kind of draw a line around it and then draw a line down it, and it would be very flat. So it's a very easy way to kind of remember what that word means. Or you could have a leptokurtic peak appearance, which is therefore very positive. So it's this one here, the red line, and lepto means slender apparently, and I assume that's either in Latin or Greek, but that's how you need to remember it. And essentially the way that we're able to calculate metrics for understanding the distribution of, the kurtosis of this distribution is by using this equation here, okay? So hopefully it's relatively familiar to you now that we want to calculate the sum of the deviations, the differences that we are raising it to the power of 4 here to get our numerator. And then for our denominator, we're taking the number of samples that we have in our sample, so lowercase n, we're multiplying it by the standard deviation raised to the power of 4. Okay, and when we've made that division, we need to subtract 3, which R doesn't necessarily do automatically, but that gives us the right metric that we need to assess the kurtosis of the data set. Okay, so if it's negative, then basically it's indicative of a more flat distribution, or if it's positive, then it's indicative of a leptokurtic, so a more slender distribution. Okay. And here I just want to emphasize that it's kind of the progression of all of those different metrics which we've now kind of covered, and that's that there are moments of a distribution, and I put down a definition here. So in mathematics, the moments of a function are quantitative measures related to the shape of the function's graph, okay? And actually, there's a very kind of specific way for us to understand that in the shape of a distribution, and kind of how we then understand probability from the shape of the distribution. So we have the first moment, which is the sum of the deviations, which is basically the mean, okay? We should know this. So it's a property of the mean, it's the numerator in the mean equation. And then we have the second moment, which is the variance, okay? So remember that we calculated the variance and we didn't take the square root of it, so we left it in its total value. And then we were able to get it from the sum of, well, from the outcome of this equation. and importantly we were squaring there. And that kind of contrasts with when we calculated the skewness, where we were taking the cube, and then kurtosis, where we were raising to the power of 4. Okay, so hopefully you can see how there's different moments in these different steps, and they help us calculate these different aspects of the graphs, of the distribution that we're interested in. Okay, so it's a nice way for us to statistically understand these different aspects and to therefore kind of extract these summary descriptive statistics. Great, well, we are done. This is the end of, I think it was the 3rd lecture on descriptive statistics. I just wanted to end on a lighter note. And that's that my friend, sorry, we're all really geeky, and my friend has this t-shirt, obviously making fun of the normal distribution, and Halloween's coming up, so I put down the paranormal distribution here just as a little way to kind of lighten the mood at the end, given that I've kind of drilled you through, you know, an hour or so of stats, which for the newbies among you might be a little bit intense, but stick with the work, and hopefully it's relatively clear. I think it will be much clearer once you finally get into the practical work, and then you should be set up to really perform well on the assignments. And then obviously with a kind of view to the first midterm, which will be in a few weeks' time, this will kind of be a kind of bedrock for what you'll be tested on within that, that particular examination. Great, well, reach out to me if you've got any questions, and then I just want to thank you all for tuning in. So have a good day, ladies and gentlemen, and I'll see you all soon. Thank you. Goodbye.